Welcome back to the deep dive. We're here to unpack the universe's biggest puzzles and bring you the science that really makes you think. And today, wow, we're asking you to really stretch your imagination. Think about the scale of the universe, just how vast it is. And then picture stars out there so enormous they make our own sun look, well, tiny. And our sun's already huge, right? Which brings us to this big cosmic mystery. How do these massive stars, these high-mass stars, get so incredibly big, especially when their own sheer power should, you'd think, be pushing away the very stuff they need to grow? It's a real paradox.
It absolutely is, and it's something astronomers have been scratching their heads about for decades, really. You've got these incredibly massive young stars forming inside these dense clouds in space, and as soon as they switch on, they become unbelievably bright. They blast out these powerful winds, intense radiation.
Right, like turning on a giant spotlight and fan at the same time.
Exactly. And logically, all that energy, that outward force, it should just clear everything out around them, like a cosmic bulldozer, basically. It should make it impossible for them to pull in any more material. But somehow, they do. They keep growing, and fast. It defies the physics we thought we understood.
That's the core puzzle, and that's what this deep dive is all about today. We're exploring a genuinely groundbreaking discovery. It really challenges the old ideas about how stars form. So our mission is to dig into some fresh research just published in Science Advances, also picked up by SciTech Daily. We want to uncover this so-called secret fuel source for these stellar giants. And honestly, the answer they found seems to have really surprised people. It hints at something much more dynamic than, the usual picture.
Yeah, the standard picture, the conventional wisdom, was always centered around these big rotating accretion disks. Like a whirlpool of gas and dust slowly feeding the star in the middle. That was the model for a long time. This new work suggests something different, something maybe more direct, and frankly, quite a bit more spectacular.
Okay, so not just those familiar spinning disks. The buzz is about these huge dynamic things called cosmic streamers, like interstellar superhighways, maybe, funneling material right where it needs to go. So today, we'll get into that paradox, how these giant stars beat their own outward push. We'll look at the amazing tech that let astronomers actually see into these hidden stellar nurseries. And then, unpack what these gas highways really mean for understanding the universe's most massive objects.
Mm-hmm. And just to give a sense of scale here, because it's important, you mentioned our sun is huge. Its mass is, over 330,000 times Earth's mass? Just mind-boggling. But these high-mass stars, we're talking stars that are at least 8 times the mass of our sun, often many times more, tens, even hundreds of solar masses.
Wow, okay, so not just big, but truly colossal. They must really dominate their cosmic neighborhoods.
Oh, absolutely. They shape galactic evolution.
What?
But it's not just their size, it's the speed they form at. That's part of the puzzle.
Right, the sources mention they form incredibly fast. But doesn't that just make the problem worse? Faster growth, more power pushing back?
Precisely. They can reach their full mass in, less than 100,000 years, which is nothing, cosmically speaking, an eye blink. And doing that, they pump out these incredibly strong stellar winds, just streams of particles flying out, and intense UV radiation. All this creates enormous outward pressure. It pushes gas and dust away. We call it stellar feedback.
Stellar feedback. Okay, so it acts like a shield, or maybe, like you said, a leaf blower, stopping more fuel from getting in.
Exactly. It should stop more fuel getting in. So the big question has always been, how do they keep getting fed fast enough to overcome that feedback? How does the material actually reach the star?
It sounds almost impossible, like trying to refuel a rocket while its engines are firing full blast.
That's a pretty good analogy, yeah.
Yeah.
For years, the leading idea was these huge accretion disks, these vast spinning platters of gas and dust. We see them around smaller sun-like stars. And the idea was material settles into the disk, then spirals in slowly, maybe shielded within the disk from the worst of the feedback.
That kind of makes intuitive sense, I guess. A more controlled delivery system.
It does, and it works well for smaller stars. But for these high-mass stars, the feedback is just so much stronger. It really should disrupt or even destroy a large disk, making it hard for enough stuff to get through quickly. And that's where this new research from this international team really shakes things up. It points to something else.
Something more direct, you said. This is where these cosmic streamers come in. I saw a quote from Fernando Olguin, one of the authors. He said, their work shows these stars are fed by streamers, which are flows of gas that bring matter from scales larger than 1,000 astronomical units. essentially acting as massive gas highways. I love that phrase, massive gas highways.
It's a great visual, isn't it?
Yeah.
And it captures the idea perfectly.
And just quickly, an astronomical unit, an AU, that's the Earth-Sun distance, right? So 1,000 AU is huge, way bigger than our solar system.
That's right. So imagine these vast rivers of gas stretching thousands of times the Earth-Sun distance. Not just gentle currents, but powerful streams, channeling material directly from the larger cloud, right towards the growing star. It's like a high-speed delivery lane, bypassing the slower, maybe more vulnerable disk system. It's got the volume, the momentum to punch through that stellar feedback.
Okay, so a totally different delivery method, but seeing something like that must be incredibly difficult. These star factories, they're super far away, aren't they? And hidden inside dusty clouds.
Exactly. That's the observational challenge. High-mass star-forming regions are typically thousands of light years away, much farther than the nurseries for smaller stars. And yes, they're buried deep inside these incredibly dense clouds of gas and dust. You can't see them with a regular optical telescope. The dust blocks all the visible light.
So how did they peer inside? What kind of technology do you need for that?
You need something special. And they use the ALMA, Large Millimeter Submillimeter Array LMA. It's in the Chilean Andes. LMA isn't just one telescope. It's an array, a network of 66 antennas working together. They combine the signals electronically to act like one enormous telescope, potentially miles across. This gives incredible resolving power, like a zoom lens for the universe.
Wow, okay. A virtual giant telescope. And why millimeter and submillimeter wavelengths? What's special about those?
That's the key. Those longer wavelengths of light can actually pass straight through the dense dust clouds that block visible light. It's like having cosmic X-ray vision. LMA detects the faint glow from coal dust and specific molecules at these wavelengths. So it lets us see right into the heart of these dark, dusty cocoons where the stars are actually being born. We can map out the gas and dust that are fueling the process.
Cosmic X-ray vision, I like that. So, armed with LMA, what did the team actually observe around this young, massive star they targeted? What did these gas highways look like?
They focused on a specific target, a young, massive protostar called G333.3 back in 3.8. Sounds catchy, right? With LMA's power, they could see details down to about 100 astronomical units, roughly the scale of our own solar system, but thousands of light years away. And what they saw was, well, pretty stunning. The protostar was clearly being fed by what looked like two distinct, massive streams of gas, streamers. One streamer in particular was very prominent. It stretched for hundreds of AU, connecting directly into the central region around the protostar.
Connecting directly. And were they just sitting there, or could they tell if the gas was actually moving?
That's the crucial part. They didn't just take a picture. They analyzed the motion of the gas within the streamers, its velocity.
Okay.
They found what we call a kinematic signature, the pattern of movement that showed the gas wasn't just rotating, it was also falling inwards. Infalling. Clear evidence of gravitational collapse, gas actively flowing toward the protostar.
So, proof of delivery. The highways are actually carrying traffic.
Exactly. And they estimated the delivery rate about 0.01 solar masses per year flowing through that streamer. That's a significant amount arriving rapidly. It's fast enough and dense enough to overcome that outward push from the star's feedback. It provides the raw material needed for the star to keep growing against the odds.
Okay, this is really painting a different picture. But here's the bit that really jumped out at me from the reports. The team went in expecting to find a big disk, right? The standard model, hundreds of AU wide. But that wasn't it.
That's the real shocker, the pivotal finding. Olgan himself said, to our surprise, there is either no disk or it is extremely small. Just let that sink in. Decades of theory built around large accretion disks being essential for high-mass stars. And they look with the best telescope we have, and maybe no disk at all. Or if there is one, it's tiny, much smaller than expected.
Wow. So the streamers aren't just helping a disk. They might be the main event, the primary fueling mechanism.
It strongly suggests that yes, these streamers seem so efficient at channeling gas directly onto the star, or very close to it, that maybe a large, stable disk just doesn't get a chance to form properly, or isn't even needed in the same way. The streamers are doing the heavy lifting, delivering the bulk of the mass required. It really changes how we need to think about this process.
So this isn't just tweaking the old model. This sounds like a potential paradigm shift for how we understand the formation of the biggest stars. Massive streamers, these gas highways being the star players, not the accretion disks we always pictured, and the lack of a big disk or finding only a tiny one, that's the smoking gun, maybe?
I think paradigm shift is fair. It suggests that for high-mass stars, accretion might be dominated by this more direct, large-scale infall via streamers, rather than the slower, steadier spiraling through a disk that we see for smaller stars. It could explain their rapid formation times and how they overcome feedback so effectively. It paints a picture that's, well, maybe more chaotic up close, but incredibly efficient overall.
And what are the broader implications? Does this change how we think about anything else in the universe?
Oh, potentially quite a bit. Understanding how massive stars form is crucial because they have such a huge impact. They enrich galaxies with heavy elements when they explode, their radiation shapes, interstellar clouds. They might influence how star clusters form. It could even affect models of planet formation around massive stars if the environment is dominated by these streamers instead of stable disks early on, and maybe even how star formation worked in the very early universe.
Okay, so this discovery opens up a whole lot of new questions. It's clearly not the end of the story. What's next for the researchers? Where do they go from here?
Right, this is really just the first step. The team definitely plans to follow up. They want to look at other regions where massive stars are forming. Use LMA, maybe other powerful telescopes coming online to see if this streamer-fed accretion is, the standard way massive stars form, or if G333.3.0.8 is somehow unusual. They also want to zoom in even closer, right around the protostars themselves, to see if there really is no disk, or just a very, very small one hiding in there. Maybe disks still play a role in the very final stages.
So mapping out more examples, checking if it's a universal mechanism, and getting even finer detail makes sense.
Exactly. Build up the statistics, refine the picture, science in action.
Okay, so as we wrap up this deep dive, it really leaves you thinking, doesn't it? We've got this fundamental process, how the biggest stars get their food, and it turns out it might work very differently than we assumed for so long, hidden in plain sight in a way until the technology caught up. So the question for you, listening, is this. If these huge cosmic delivery systems, these gas highways, were operating kind of under the radar, what else might be out there? What other incredible, unexpected processes or, I don't know, cosmic infrastructures might be quietly shaping the universe, just waiting for us to find the right way to look? Makes you wonder what other surprises the cosmos has in store.
It absolutely does. It's a great reminder that there's always more to discover, always assumptions to challenge. The universe is full of surprises.
Couldn't agree more. Well, thank you for joining us on the deep dive today. We hope this journey into the birth of giant stars has sparked your curiosity as much as it has ours. Until next time, keep looking up.